Well, welcome to 5.2 and 5.3. Now begins the trigonometry, really kind of in depth. The trig course is kind of a major class that just a bunch of stuff is going to carry out through a variety of different topics. You'll see a bunch of trig in calc, and this is one of those major topics. So the things that we're going to be doing in here that you need to be able to do is to find the trig ratios and to find the trig functions using a circle, and that's where this idea of circular trigonometry comes from. So we're going to be doing right triangle and circular as well. So just to kind of get you started on this, I'm going to start with an equilateral triangle. You don't need to write this down, just kind of understand something here. So an equilateral triangle has some things that are true about it. What makes it equilateral is all the sides are the same, but in addition to that, all of the angles are the same. So you got 60 degrees in each of the angles in an equilateral triangle. So equal sides, equal angles. Just for fun then, I'm going to drop in a perpendicular line straight down the middle. Now this line is going to do a few things. One of the things that it does is it bisects the angle up at the top, and it also bisects the side at the bottom. And so what I create in here is a triangle. And this triangle, I'm going to pull it over here. Notice that this length was x out here. This one is going to be half of x. And then I'm going to do a little Pythagorean theorem to figure out what this missing side is. So on that missing side, I'm going to do a squared plus I don't know squared is equal to x squared. And when you solve that equation, what you get is that the missing side, this vertical length right here, which by the way is called the altitude in that triangle, is 1/2 x times the square root of 3. You can double check the arithmetic here. So what that creates for us is a pattern of these three sides, that side's this one, on a 30, 60, 90 triangle. And this relationship looks like this, that if you know what the hypotenuse is, now I'm doing it in two different ways. The side across from the 30 is half of the hypotenuse. So here's the 30 degree. Across from that is half the hypotenuse. In this picture, if this was 2x, the side across from the 30 is half of that number. Then the side across from the 60 is that number times the square root of 3. So in this case, that number times the square root of 3. So know this sentence. The side opposite the 30 degree angle is half the hypotenuse, and the side across from the 60 degree angle is half the hypotenuse times the square root of 3. So what that gets us is certain relationships in right triangles. Specifically though, this only applies to a 30, 60, 90. So if you got 30 degrees here, then this is and that's 90, then that's got to be 60. And so the side across from the 30 is going to be half the hypotenuse. And the side across from the 60 is going to be half the hypotenuse times the square root of 3. So the A is just simply half the hypotenuse, 5 in this case, and then the B is half the hypotenuse times the square root of 3. Simple as that. Set it up a little bit differently. So now what I'm giving you, this of course then would be the 30 degree angle down here. And so that's the side across from the 30. It's half the hypotenuse. Well, then you can figure out that C has to be 14. And then the side across from the 60 is always that number times the square root of 3. Here's where it gets a little trickier. So what if the side across from the 60, which is half the hypotenuse times the square root of 3, what if it's a nice even number? Well, solve this equation for B. So I'm going to multiply both sides by 2. That's how I got 16. And then divide by square root of 3. Then I rationalize the denominator over here. And so what that means is B, the hypotenuse, would be 16 square root of 3 over 3. And then the A is just half of that. And half of 16, square root of 3 over 3 would be 8 square root of 3 over 3. All right, there we go. Yeah, already got that. Okay, so another one that you need to know. What we just dealt with was a 30, 60, 90 triangle. We started with an equilateral triangle. This time I'm going to start with a square. Of course, with a square, all four sides are the same, and you got 90 degrees in each of the corners, right? So I'm going to drop a diagonal in, and what I create when I do that is a 45, 45, 90 triangle. Those two triangles, the 30, 60, 90 and the 45, 45, 90, are in the category of must know. You must know these relationships. So in a 45, 45, 90 triangle, the legs are always the same length. And so they're always column X if you want. Now I'm going to use these two sides to figure out what this missing side is over here. And I'm going to do another Pythagorean theorem. So as it turns out, C is whatever that length is times the square root of 2. So if you know the relationship in the 45, if you know one of the sides, you know the hypotenuse is that number times the square root of 2. Now, as it turns out, and I didn't spend time showing you how this happens, but if you happen to know the hypotenuse, then the legs are half of that length times the square root of 2. Half of that length times the square root of 2. So let's look at a couple examples. Here, I know one of the legs, so if that leg is 5, then of course A has to be 5. And here I know the hypotenuse. So then, as I said, A has to be 5. And then the hypotenuse is x, and x square root of 2. So 5 square root of 2. A little trickier over here is if I know the hypotenuse, then the legs are half of that times the square root of 2. So x was 9. So 9 over 2 times the square root of 2. That's the length of the two legs. 9 square root of 2 over 2. And just leave it like that. That's fine. So, be able to recognize immediately which pattern you have to use. Here, this is obviously a 30, 60, 90. This is going to be a 45, 45, 90. And then just use the what you know about them. I'm sorry, I'm flipping back and forth. I have a different example there for some reason. So let's do this one real quickly. So, I'm sorry, that's what this was. They were just different examples. I just didn't have it written out. So in this problem, if I know that this is a 30, 60, 90, then the side across from it is half, so 21 over 2. Just leave it like that. And this is 21 over 2 square root of 3. Here, if I know one of the legs, then the other one's also going to be 7, and this is going to be 7 square root of 2. Let's try that example on your own. And got those worked out. You can pause that. I'll let you look at that one here real fast. Look at this one real fast if you want to. So, okay. So now a little more into the trig. Now we're obviously getting into the circular trig. In the trigonometry you had in the past, you know that the relationships have to do with the sides of the triangles and an angle. Well, I'm going to take a right triangle and I'm going to superimpose it into a circle. And so instead of calling this the hypotenuse, I'm going to call it the radius of the circle. When we do trigonometry, what you have to understand is that it's a comparison of the sides to each other. Now, if I only write two at a time, how many different ways can I write A, B, and C as a fraction? For example, A over B would be one way. A over C would be another way. Well, keep playing around with that. Turns out there are 1, 2, 3, 4, 5, 6 different ways you can write these three sides as a fraction. Well, that's why there are 6 trigonometric functions. They are simply looking at those three sides as fractions. Now, if you remember your old trig, back from Algebra 1 and Algebra 2 days, the sine is defined as the opposite over the hypotenuse. So if I have this angle down here, the opposite would be y, and the hypotenuse would be over here, which we're going to call r. So instead of calling it opposite and hypotenuse, I'm going to change the names to x, y, and r. So the old SOHCAHTOA gets translated into these values here. And the reason we do that is that opens up some possibilities to bigger kinds of pictures, bigger triangles. It used to be that the angles we dealt with always had to be acute angles, but now you can have obtuse angles as well. So the opposite side is, let me delete these out real fast. The opposite side, when I'm dealing here with this angle, would be the y value, and the adjacent side would be the x value. The adjacent would be x. And the tangent, y over x. The other trig functions, or if you remember the list we had, for example, we had like a over b, but one of the other ones was b over a, that's just the reciprocal. So the cosine's reciprocal is the secant. The sine's reciprocal is the cosecant, and the tangent and the cotangent. The way I remember those is the opposite letters go together. That's what I'm showing you here. C and S go together, C and S go together. So the reciprocal of the sine, cosecant. When you look at that graph I had, and I'm looking at y value and an x value, and this is r, the secant, which is the reciprocal of the cosine would be x over r, so the secant would, I'm not sure I said that right, the cosine would be x over r, so the secant would be r over x, just the reciprocal. So let's play around with this a little bit. If the secant of theta is equal to -2 and the sine of theta is less than 0, find the other 5 trigonometric functions. Well, here's a key thing here. Sine now is, I can be negative, and the reason that I can get negative answers is because now when I'm dealing with y value over the radius, that's the definition of the sine, the y values are negative somewhere down here. So that means that this angle theta has to be somewhere either in the third or the fourth quadrant. Secant's the reciprocal of the cosine, and if the cosine's negative, that means the x value has to be negative. Because the radius of a circle is always positive, this is where the negative has to come from. The cosine's negative anywhere the x values are negative, and that happens either here or here. So that's what tells you that this picture has to be somewhere in the third quadrant. So let's draw in an angle down in the third quadrant. Then we drop what's called a perpendicular, and we always go back to the x-axis and create the reference triangle in the third quadrant in this case. And now I'm going to label sides. Now remember, the secant's the reciprocal of the cosine. Cosine is x over r, so this is r over x. And what you realize, r value can't be negative, so I have to think of it this way, r over x. So the x is -1 and the r is 2. Well, little Pythagorean theorem, look, this side is half the hypotenuse, that must be 30 degrees, which makes this 60 degrees. And so side across from the 60 is that number, this number, times the square root of 3. That's how I found this down here. Inappropriately, I did not put the negative there. That should be a negative sign on that point. So, yep, there's the reference triangle. Catching up to my notes here. And there it is. This time I've got the negative on there. So now the question was, back with this problem, was to find the other trig functions. So look at the picture. I know that r is 2. I know that x equals -1 and that y equals negative square root of 3. X, y, and r. And so bring those over, just put them down, somewhere off to the side, and now you can fill in the blanks on every one of these. We know the sine is the y value over the radius. Cosine is the x value over the radius. And just work your way filling in the blanks. If the terminal side of an angle theta goes through the point -815, find the 6 trig values of theta. Well, let's draw a picture. So -815, that's -8 for the x, 15 for the y. A little Pythagorean theorem gets us that r is 17. Well, now I've got x, I got y, and I got r. You fill in all the blanks. You can pause that and look at that for a few moments. Secant of theta. Secant of theta is equal to the square root of 3. Theta is in quadrant 4. find the other 5 trig functions. So let me draw a picture. I know that the secant is the radius over the x value, right? Reciprocal of the cosine. So the radius is square root of 3 and the x value is 1. Well, a little Pythagorean theorem will get you that the missing side is square root of 2. Now, just fill in the blanks, keeping in mind this is a negative number, this is positive, and the radius is always positive. And so then you just take those 3 things and write the remaining 5 trig functions. So now a little more generic. Let's find the sine of 30 degrees. Well, a 30-degree angle would look something like this. That's 30 degrees. I always start on the positive x-axis. That's the initial side. And then I drop a perpendicular straight down, and I create a 30, 60, 90 triangle. You get to pick whatever radius you want. I am always going to pick a radius of 2 out here. There's nothing magical about that. It's just easier to work with. So I pick a radius of 2. You could pick any number you want to. But in a 30, 60, 90 triangle, the side across from the 30 is half the hypotenuse, and the side across from the 60 is that number times the square root of 3. So there's your 3 sides. X is this, y is 1, r is 2. Sine is defined as the y value over the radius. So the sine then, once I've got these labeled, I just pull out the number. The sine is the y value over the radius, and that's, whoops, did I change? Yeah, sorry, here it is. Sine is 1/2. If I wanted to find the cosine, that's what's happening on this page. If I wanted to find the cosine, it's just square root of 3 over 2. Let's do cosine of 60. Well, I'm going to keep that radius at 2. It's just easier. This is 60, which makes this 30. Side across from the 30 is half the hypotenuse. Side across from the 60 is that number times the square root of 3. There's the 3 pieces of information I need to figure out the cosine. Cosine is defined as the x value over the radius. Look at that. Cosine of 60 was 1/2. Sine of 30 was 1/2. They both have the same answer. Sine of 60, though, is the y value over the radius, so square root of 3 over 2. Let's do 210, so a little different. So I'm still going to work with this radius of 2. Again, you can pick any number you want to, it doesn't matter. And so at 210, I know that this is 180, which means this is 30 degrees. And so what I've created is a 30, 60, 90 triangle. So side across from the 30, if that's the 30, the side across from it is going to be half of that. That's going to be, since this is 2, that's going to be 1. And then the side across from the 60 is that number times the square root of 3. Be careful about the negative signs in this quadrant. The x value and the y value are both negative. And so the sine of 210, well, the y value over the, oops, wrong one. Y value over the radius is negative 1 over 2, or negative 1/2. So when we introduced the radians to you, it opens up this whole other category. I'm going to leave this off for right now, but these are questions that you need to be able to answer. Let me go through the rest of the notes so you can see this. You can pause this if you want to figure things out. But at this point, I'm not going to include this in the notes quite yet for this section. And that was the last little bit. So hopefully you got some good information there, and hopefully it'll help you work your way through